Okay. Today let's start with the with a little bit different topic regarding the Laplace transform. Let's briefly mention about the theoretical inversion of the Laplace transform, and that is something that we're not going to use in a way. We will use the Laplace transform inversion using the tables and our properties, basically. We will try to write down the numerator over denominator polynomials by expanding into first order and second order systems, and from there we will try to invert the Laplace transform. So the trick is we want to make the Laplace transform similar to something that we already know, and that's how we can invert the Laplace transform. But nevertheless, there is at least a concept of theoretical inverse Laplace transform, and that theoretical inversion comes from the formula, as you may guess, x of t times e to the minus sigma t, which is the real function related with the Fourier transform, is the inverse Fourier transform of x of sigma plus j omega. So what I mean is this. Remember that the Laplace transform x of s, which was x of sigma plus j omega, was something like this. It was from minus infinity to infinity x of t e to the minus sigma t e to the minus j omega t, with a t parenthesis and dt, of course. With the t parentheses, we had sigma plus j omega, which was abbreviated with an s parameter. So what we are doing here is we are assuming that this portion is the real function which we take the Fourier transform. That's why x of t times e to the minus sigma t is the inverse Fourier transform of x of sigma plus j omega, capital X of sigma plus j omega. That's where it comes from. And from here, we can write the inverse Fourier transform formula like this, with a 1 over 2 pi coming from the inverse Fourier transform, an infinite integral e to the e to the j omega t d omega. Let me first write it like this, and then we must have e to the 1 over e to the minus sigma t, which is e to the sigma t, isn't it? So that's what I will put inside the integration, and the integral will automatically become like this: x of sigma plus j omega e to the sigma plus j omega in parentheses t d omega. Or you may just replace sigma plus j omega with an s, and it will become capital X of s e to the st d omega. Now, so it's not ds anymore, it's d omega. But d omega is a line on the s plane. So this is x of s, and this is e to the st. But this one is d omega. So we are taking the integration, this integral, on the omega axis, in other words, j omega axis. Or we can write it like this. Let's make a substitution, replacement of variables. Let's try to make a change of variables, saying that s is equal to sigma plus j omega. Therefore, s minus sigma is equal to j omega, and omega is equal to 1 over j S minus sigma. You can write it in this form, which makes our integral with these change of variables like this: 1 over 2 pi j, an integration, and this integral is along a shifted line this time. It is not from minus infinity to infinity for omega, it is from sigma minus j infinity to sigma plus j infinity. So don't get confused about these concepts. This infinity or j infinity corresponds to the minus infinity of omega. This is sigma minus j omega. J omega at omega is equal to infinity. This is sigma plus j omega at omega is equal to plus infinity. So they are both sigma plus j omega, in other words. S is equal to sigma plus j omega, as you see. And along these, along this line, we can write x of s e to the st ds. Therefore, this new formula, unlike the top formula, with the change of variables, it lets us to evaluate the integral along a line which is different from precisely j omega axis. Normally, as we know, we have a region of convergence with a real and imaginary axis, and the region of convergence is a stripe. It may be somewhere. I'm just assuming that this is the region of convergence. Normally, since the Fourier transform doesn't exist, we are unable to evaluate the inverse Fourier transform from this expression because the j omega axis is not included. If it is included, you are safe. Just replace s with j omega, assume sigma is equal to 0. In other words, in the term of sigma plus j omega, assume sigma is 0. Then you evaluate your integral along this line. But as you see, it is not in the region of convergence for this case. So what you do instead is a shift, and you evaluate the integral along a line somewhere here with a certain sigma that stays inside the region of convergence. That is where you evaluate the integral, the top integral over there. That is the theoretical way of evaluating the inverse Laplace transform. And it's a concept of complex calculus, basically. And in the complex calculus courses, I'm not sure whether you have thoroughly covered the complex calculus. It used to be a mandatory course in the previous years, but now it has changed a little bit. If you have a line integral like this, from minus infinity point to plus infinity point along that line integration is evaluated by the inverse Laplace transform. So it's the other way around. You don't evaluate the inverse Laplace transform using that integral, but you evaluate that integral using Laplace transform inversion. Because that line integration is something too hypothetic. So how are we going to evaluate that integral? We evaluate it using the tables of the Laplace transform. So let's forget about this hypothetical concept of inverse Laplace transform for the time being, and let's focus to how we can really invert our Laplace transforms. And we know it already, right? Let's see an example. So we're not going to use it this way. It's just the other way around. I have to repeat. We are going to evaluate that integral using simple tables like this. Assume that you have a Laplace transform x of s given to be 1 over s plus 1, s plus 2, with a region of convergence given as, by the way, this region of convergence is quite the intuitive or easy region of convergence. It's to the right of minus 1. So what is the causal or right-hand sided inverse Laplace transform is the question. If you try to use the above formula, you will fail. If you try to use the full inverse Fourier transform, you are safe. You can use the inverse Fourier transform because real part of s greater than minus 1 includes the 0 sigma line, which is the j omega axis. So just replace s with j omega and you will take the inverse Fourier transform. Easy. But you don't even need to do that. Instead, as we did for the Fourier transform, we just try to separate this into two first order systems like this, and we solve for a and b. So how do you do that? You multiply this by s plus 2, this by s plus 1, and you say that as plus 2a plus bs plus b is equal to 1, which means a plus b is equal to 0, because as plus bs should give you a 0s. There's no s. You have two formulas coming from there, and 2a plus b is equal to 1, which makes a is 1, b is minus 1. So our x of s is equal to 1 over s plus 1 minus 1 over s plus 2. As simple as that. And the inverses of these are evaluated. They must be evaluated as the right-hand sided solutions, inverses of each of them, because the overall region of convergence is the intersection, which is to the right of minus 1. So the inverse of this one is e to the minus t u of t minus e to the minus 2t u of t. Or you may put into parentheses of u of ut if you wish, and say e to the minus t minus e to the minus 2t. E to the minus t e to the minus e to the minus 2t ut, like this. So this is the inversion. Whenever you have the possibility, you should do it this way. Okay? Whenever you can do it. And I'm promising you, I promise you that at least in the exams, you will have a Laplace transform inversion. You may have a Laplace transform inversion in a similar concept. It may not be as easy as this one. It may require utilization of other properties that we will see. We haven't seen them yet. But use the properties and try to invert them that way. Do not try to evaluate that integral, that complex. Really? Why? You don't need to do that. Too bad. Because the Fourier integral is a subset of that one, which is an easier subset. So in order to solve an easier subset of a question, you consult to a more difficult subset, which is a complex line integral. Very strange concept, very strange topic. So try not to do that. And as I say, this is the solution for the region of convergence definition, real part of s greater than minus 1. It could be like real part of s is less than minus 2, and in that case it doesn't correspond to a Fourier because it doesn't include the j omega axis, and you will find x of t to be equal to minus e to the minus t u of minus t, sorry, u of minus t plus 2 e to the minus 2t u of minus t. Another case, and just another one, minus 2 greater than real part of s less than minus 1. So real part of s is between minus 2 and minus 1. This is also something which doesn't have a Fourier transform. Nevertheless, it has Laplace transform inversion corresponding to the right hand sided version corresponds to the pole with -2. So let's make it as it is, which was -2 e to the -2t u of t, and the other one would be left hand sided, therefore it must be minus e to the -t u of -t, and this will be x of t. Okay, you can solve it that way. As you see, we didn't do anything. We're not doing any kind of fancy integrations or anything. We're just converting the system into first order systems. In some cases, there may be parentheses square versions, those or s square plus a square sort of expressions. In those cases, it corresponds to a double-sided integral. Okay, that may be the case. You can find it that way. If you remember, we have solved a question like e to the a times absolute value t. Okay, which was double-sided. There was no u of t. Now that would make a second order system which cannot be split into first order systems. So it can either be in a parentheses square or first order systems like these ones. We will try to solve a few more examples for inversion, but nevertheless the book by Oppenheim, at the back side of the book, the immediate questions, the first questions are: find the Laplace transform of these, a lot of signals, and then find the inverse Laplace transforms of these, a lot of Laplace transforms. Try to solve them, and in case you fail to apply the properties like this, that would be a good indicator for you. Okay? Those are the ones which you have to invert in the Laplace transform to time domain conversion. Now, we will come back to the properties later. The next thing that I want to mention was with an applet. I used to have that applet under my web page, but since I don't have a web page now, which I can totally control, in order to insert a Java applet, unfortunately you have to have admin privileges to go and install the Java software inside the server. Now they just provide us with some plain HTML versions, therefore I cannot insert an applet. But try to find something similar. I didn't really check for that recently. Those applets are quite beneficial to understand the concepts, but without that I'll try to explain just by drawing. System response from poles and zeros is the topic that I want to explain now. What I mean by that is something like this. If you have poles and zeros located on the S-plane, they can be just anywhere. I will just arbitrarily draw some poles and zeros. As you see, since they are not in conjugate pairs along the imaginary axis with respect to the real axis, this cannot be the Laplace transform of a real system, or it cannot be the Laplace transform of a real signal. If it's a real signal, then this must be just the opposite, the conjugate, the mirror symmetry. This one must also be like that, this one must also be like that, this one, etc. But these are not like that. So this is too arbitrary. Strangely, the applet that I used to have had that option of when you insert a pole, it was symmetrically inserting the conjugate pole as well, okay? And the zeros. But nevertheless, if it is like this, it's also possible, hypothetically at least, it may be a complex system. This is, as you may remember, the imaginary axis was also known as the j omega axis, and this is the real axis, as we know, which is the sigma axis. Now, what I want to derive from this pattern is within a scale, regardless of the scale, it may be multiplied by a constant. What is, if this is, for example, h of s, the pole and zeros, what can we say about the magnitude of h of j omega? How can we plot this from these poles and zeros? Now, h of j omega, as you see, is h of s evaluated along j omega. So we are interested in points, for example, this point, along the j omega axis. For a certain omega value, this any point on the imaginary axis is the omega value, the frequency value. And why are we interested in the magnitude of h of j omega? Because it describes us the characteristics of the system. It may be, is it a low pass filter, is it a high pass filter, band pass, etc. They are all determined by the shape of that. If it is like this, for example, in the central frequency, around zero frequency, it is some magnitude and then decays down to zero, then what can we say about it? It's a low pass filter also. So this shape is important. The question is, from this whole zero pattern, is it possible for us to estimate this magnitude of h of j omega? And the answer is quite an easy yes. Let me draw it with red. What we need to do is we need to find the distances from the poles to that omega, to that frequency point. And we need to repeat it for all frequencies. We are just like holding a mouse and dragging this point downward and upward. And we are measuring the distances from the poles to that point. Of course, it will not only be the poles. For example, this distance, and this distance. These are, let's assume, D1, D2, and D3. Three distances because we have three poles. And we have also distances from the zeros. The distances from the zeros, let's assume them to be n1 and n2. This h of j omega will be equal to a constant which doesn't change the shape. It's just an amplification of the system response times n1 times n2 over d1 times d2 times d3 if you have two zeros and three poles. So this is the whole idea. You are measuring, you have to measure the distances from the zeros and put them in the numerator, and measure the distances from the poles and put them in the denominator and multiply them. If you just move that omega downwards, as you see, the distances will change like this. And correspondingly, the values of these will change. And you have to just follow what sort of a shape it produces. This h of j omega produces, the magnitude of h of j omega produces with respect to the changing omega. If it is, for example, increasing as we move omega around zero, if it increases somehow, then it is a low pass thing. And as omega goes to plus infinity, minus infinity, or plus infinity, is this term or that term shrinking down to zero? If it is shrinking down to zero, we can say that it's behaving to have a characteristics of a low pass filter. It may have some high pass characteristics, band pass, band reject, etc. That applet, this is the third time I'm referring to that, was a very versatile tool, very useful tool to design filters as well, because whenever you insert poles and zeros, by dragging that omega upward or downward, it was tracing on the magnitude of h of j omega, and you were designing the filter. By insertion of a different zero, you may make it a sharper low-pass filter sometimes, or a poorer low-pass filter. Let's make it a band-pass, band-reject filter. You were just inserting poles and zeros for that. But you may guess that making a low-pass filter could be something like this. I wish we could have that. Suppose we have these poles. Let's have 5 or more poles. Let's have more poles. So we have 7 poles, and then we have four zeros. I am trying to make a low-pass filter here. Okay, you may or may not understand why. These zeros, if you insert some zeros along the j omega axis, that's a very nice trick to apply, because it makes the magnitude of h of j omega, the top expression, to become identically zero at these frequencies, because the distance n1 here will be zero, or here, or here, or here. So the numerator distances will be precisely zero. They will touch zero. So when you try to draw, hopefully, I'm not sure about this, I'm sorry. The low-pass filter that I was trying to, what is that? Get was something like this. Something like this. And as you see, this frequency is the frequency corresponding to somewhere here, let's say. And this frequency is somewhere here. So they touch to zero. I'm suppressing them. I'm trying to suppress them as early as possible to make it a relatively sharper downward grain with good quality factor, a low-pass filter. Now, here are some questions. Why did I try to make the number of poles more than the number of zeros? Look at the expression. No. Look at the expression. As you see, we have to deal with all of the distances from the zeros in the numerator divided by all of the distances from the poles in the denominator. Let's try to find what happens as we go to minus infinity. As we go to minus infinity, the differences from the zeros will be infinity. It will be 4 times infinity, sort of. Sorry, infinity to the power 4. They will be in the numerator, infinity to the power 4. From the poles, it will also be infinity, the distances, but there are 7 of them. So it will be infinity to the power 7 in the denominator. So which one is stronger, the numerator or the denominator? Denominator. That's why as we go to minus infinity and as we go to plus infinity, the magnitudes will decrease, it will shrink. And that's a necessary condition to obtain a low-pass filter. If the number of poles and zeros are equal, at infinity, these tails will go to a level, not 0. It will be a c times 1. That constant level, it will go to a constant level. If the number of zeros is more than the number of poles, then it will diverge to infinity at both tails. in order to suppress them, we must have more poles than zeros, like this one. And here I observe a peak. What can that peak be? That peak is a frequency value somewhere here, which is nearer to a pole. As you become nearer to a pole, since that distance, for example, the distance from here to here, that distance will become small and it's in the denominator. So a small distance in a denominator will make the amplitude larger. That's why you observe a peak here. And this frequency here is something like this frequency here, which is nearest to this pole, for example. We have another peak here at the zero because there is a pole which is nearest in the distance to the j omega axis at omega is equal to 0. So, for example, as another example, if you have a situation like this, now what kind of behavior would you expect? You would expect a peak somewhere at minus omega 1, minus omega 2, let's say. At minus omega 1 you observe a peak. At minus omega 2 you observe a peak. At 0 you observe another peak. Because the distances will become too near. Around here, etc. Of course you have to properly locate the zeros with respect to this one as well. Okay, so this is a nice way to visualize the behavior. Another example. What would you say about this? Okay, let's make them equal. So 5 poles and 5 zeros. This must be a high pass filter, I guess, because around 0, around the low frequencies in this range, things are suppressed. They are made 0. And as we come here, it will make a peak and another peak, and at infinity it will stay in a constant value because the number of poles and zeros are the same. They are both 5. So I expect that the situation is something like this. Some sort of a high pass filter. But I'm not quite sure about the overshoots, the fine tunings and all these things. Okay? It's just the shape that I'm describing. Can you design a band pass filter now? So this may be a band pass filter. Why do I say so? It's first of all, the number of poles is more than the number of zeros. I try to do it that way. If it's not enough, let's put another pole here. Let's make poles even more, to make sure that at infinity it goes down to 0. Then at some point it increases and stays in increased level. They are the frequencies around here where the frequencies are nearer to these poles. They increase. And then towards here they become this time nearer to some zeros. In fact they touch the zeros, so they go down. So the shape is down, then increase, and going down again. So that's a bandpass filter. So is it sharp enough or whatever? I don't know. But this is the idea. This kind of a tool is the fundamental of, it makes the fundamentals of filter design in signal processing. People who know signals and systems, signal processing, well, if you know that, your boss may ask you to design a filter. And the way to design a filter is to locate the poles and the zeros to satisfy your shape. Then, of course, you have to proceed further, because it's not only signals and systems that an engineer must do, you must also implement it. What is the order of this? It is the 8th order system, it looks like, because there are 8 poles, which means you must use at least 8 capacitors and inductors if you are trying to implement it with a circuit. It's a combination of 8 first order systems, perhaps. I'm not very keen on those implementations, but I can at least design the structure in this way and then give it to another engineer who knows circuit theory better than I do. So they may proceed that way. So this is the system response. But I haven't mentioned one thing. I have only mentioned about the magnitude response. These poles and zeros automatically describe the angle response as well, which is the angle of h of j omega. But that's not a critical issue for the design. We are not usually interested in the phase of the system. We are more interested in the magnitude response of that. And the reason for that is both the human ear and the human eye are insensitive to phase distortions. A phase is a sort of delay within a period, and human ear cannot notice the difference. If it is low pass filter, then the treble sounds are gone. If it is high pass filter, then the treble sounds are amplified and lower frequencies are attenuated. So people are not very much interested in this angle term in several cases, but to be precise, we need to know it as well. And the thing is, the angle is the tangent inverse of which is this angle, by the way. So how can we write it? Alpha 1, let's call it. No, let's not write it as tangent inverse. It's alpha 1. And from here, alpha 2 is a little bit awkward. It's like this, alpha 2. So this angle is alpha 1 plus alpha 2, which are the angles of the zeros, the numerator terms, minus the angles of the denominator terms. Beta 1 minus beta 2 minus beta 3. So you have to measure these angles. Let's see one example at least of how to find both of them. We have two important examples actually. One of them is first order, the other one is second order. The first order system is like this. H of t is equal to 1 over tau e to the minus t over tau u of tau. And you must notice that this system with this kind of an impulse response is a system with one capacitor and a resistor. It's a decaying exponential with a time constant. First let's find h of s. H of s is equal to 1 over s tau plus 1, where the real part of s is greater than the pole, which is at minus 1 over tau. So this is the Laplace transform. So let's put a pole at minus 1 over tau somewhere here. We have one pole. If you don't have a 0, you may just assume the numerator to start with a 1. Okay, it will be 1 over this thing within a scale. So at this point of omega, let's assume, and this is minus 1 over tau, what is this distance and what is the angle of that? Quite easy, as you see. That distance is the hypotenuse of a triangle, and that triangle has sizes 1 over tau. So the denominator, the distance is, or distance squared, is 1 over tau squared plus omega squared, which makes d is equal to square root of 1 over tau squared plus omega squared. That is the denominator, and we can say that magnitude of h of j omega is equal to a constant times 1 over tau squared plus omega squared. This is the magnitude, we can say. And the angle of h of j omega will be the negative of tangent inverse of omega over minus, sorry, it's not minus, it's, the angle is from here, so it's plus 1 over tau, and that would be minus arctangent of tau times omega. So that would be the angle, an arctangent expression with respect to omega. Now let's try to verify this one. This is just an example regarding the angle, but this expression I told you to be that way, but let's at least make a verification, one single verification from here. From here, h of j omega we can write, because the pole is at the left hand side and it is causal, so it includes the j omega axis, so we do have a Fourier transform here, and that Fourier transform, in fact, if we don't have a Fourier transform, sorry about that confusion, if you don't have a Fourier transform, then you cannot talk about this. If you don't have it, then what's the magnitude of something that you don't have? Of course, it must assume that you have the Fourier transform. And that Fourier transform, h of j omega, is 1 over tau j omega plus 1. And from here, what is h of j omega magnitude squared? You can find it. You can find the magnitude squared. And you will find it to be equal to 1 over tau squared 1 over omega squared plus 1 over tau squared. You will find it like this. This will be the magnitude square term. And when you take the square root of that, h of j omega will be equal to 1 over tau times 1 over square root 1 over tau square plus omega square. Now, are they the same? This one, that one. They are indeed the same. What I just couldn't discover from the pole zero localization is this constant coefficient C over here. Within a scale, I said, that is providing us with the shape. But from here, of course, that scale is also given. It is 1 over tau. C is 1 over tau, which I just couldn't find. And you don't really need to find it, because you can always amplify or attenuate your systems. The shape of that is important. Low pass, band pass, high pass, etc. So this is a verification. 1 over tau is the constant. Yes. Which we called it previously C. Something that we didn't know. Now we know it's 1 over tau. I may give you some graphs, and I may ask you to roughly estimate the shape from here. So at least you should be able to tell me whether it's a low pass, band pass, high pass, band reject, or some different shape. Roughly, you should be able to indicate what kind of a filter it corresponds to just by looking at the poles and the zeros. All right? We will continue with the second order system example, but let's give a break of 15 minutes first. Later we will continue.